All right. We'll keep this lecture somewhat short because I don't want to get too much into live loads without having the time to discuss it. The live load provisions, but they can be a little involved. So I want to take my time on that. But the dead load example, I really think we can finish that quite quickly. So I want to go ahead and take care of that. Your team member evaluations, I think I've only got 3 of them. I need the rest of them today. Your individual evaluations of each other. Like I said, I think I've gotten 3 of them. Week 4 meeting minutes. I graded your week 3 meeting minutes like right before I came in here. They're great. I didn't have a problem with them. Keep it up. Week 4 is going to be due Wednesday. I thought I would mention this. They're going to be due Wednesday, but I'm not going to be here Wednesday because I'm going to be in Iowa. So we are canceling class on Wednesday. So we'll discuss some stuff associated with live loads on Monday. And then Friday, we may continue the discussion of live loads, but I don't want this to be just a pure lecture-based class. I mean, at some point, maybe we ought to, have a powwow about your submissions, and see where everybody's at. How are you feeling about your submissions, your alternative designs? Are there any concerns, any questions, anything like that? I did get your team's 2 RFIs. One of them, remind me, there was one on loads and one on hydraulic information?
Yeah.
Okay. The hydraulic information is on the conceptual drawing. Did you?
Yeah, I looked at it, but I couldn't determine what I needed.
Well, one of them was the normal water, one was the high water.
Yeah.
What else did you need?
It's the river channel is what we use for any kind of traffic, like boating, station on the water.
No, there'll be a couple folks fly fishing it. That's about it. Okay. No, I'm serious. It's a little more than a creek. So.
I just wasn't sure because there's certain standards that require different things.
I mean, look, you can do the math and you'll find that the creek as a whole is like, I want to say it's like 20, 30 feet wide. I mean, to say it's a creek is pushing it,
Yeah. Well, the only reason I was wondering is because it kind of determined what we...
It's a glorified ditch.
Oh.
Oh. You're talking about for the 1 to 2?
Yeah, because like I needed to figure out how to calculate that so we can figure out where we're going to put our piers if we use piers, because you can't put piers inside the water level.
Yeah. Well, I'll get back to you. And then the other one was on live loads. That one I will respond to in detail.
Okay.
And I'll try and get you something soon. But we haven't even talked about live loads in general, so, But I did like your format. I thought that was nice, I thought you were as specific as you should be or as you can be at this particular instance, so that was cool.
Are you able to use the access to the group email thing that I set up? I set up a group inside the live that has a group email.
Yeah, do like Office 365. So you can do like, and everybody in the chain. I know it's like a file kind of thing, but anything that gets, if you reply to even just one person in the group, it's like a group email address to everybody.
That's pretty cool, actually.
It's only private to whoever's in the group.
That's pretty cool. I will, no, I didn't see it. I saw your PDF, like I read the PDF, and then I had it in my head, what I was going to say, for the most part, and then I didn't look at that, though. That's pretty cool. I might have you show me that before the semester's out, because for senior design next semester, we're going to have like 20-some people in there. So,
Okay.
yeah.
It's pretty easy. I did it in like 2 minutes.
Okay, all right. I'm intrigued. Okay, any other general questions about, like, the project, life, Marshall?
Don't get started on Marshall.
Yeah, I will, yeah. Okay. Is it just me, or is it a little toasty in here?
Well, you could look at the heat pressure.
Hey, I'm not, I was gonna, let's say at least the alarm's not going off in the main hallway, and then as soon as I say that, boop, boop, Okay, let's continue our discussion of dead loads. So ultimately, what we're trying to determine is all of the associated dead loads for this given bridge. We split this up into DC1, DC2, and DW. We'll do the DC2 DW later. They're actually pretty straightforward for a bridge like this. But the DC1, there's a lot of different components, okay? So there's the girder, the miscellaneous details, the slab, and then we did the fillet, and that's where we stopped, right? Okay. Now there's one more component to the slab that I want to discuss, and that's the overhang taper. So let's take a look at that. Okay. So I'll do my best to try and draw this appropriately. Hold on. Goodness. Okay. So when I say the overhang taper, what I'm talking about is this part right here, this red sort of hatched shaded region that you see right here. We have to compute the weight of this. Okay? Now, here's some dimensions that we need to consider. Okay? This dimension right here, which is from the center of the girder to the edge of the deck, is the overhang. And this overhang is 42 inches. Okay? Now I'm getting that from right here on the top right. Does everybody see that? This is 42 right there. 3'6", that's 42 inches. No, that's a good question. That is, in my opinion, that's a little wide. But when you are proportioning your cross-section, okay, a good rough estimate for your overhang is your overhang should be about somewhere between high 20s to mid 30s% of your girder spacing. So if you got a girder spacing that's 10 foot, your overhang should be probably somewhere in the 3-foot range. Okay? So what you can do is you can say, okay, if I got, this many lanes, I got this many, two shoulders that are this wide, and room for the jersey barrier or guardrail or whatever you decide to use, what have you, you can determine the road width, all right? Then if you say, well, if I'm going to use 4 beams, well, I got 4 beams, I got 3 spaces, and then I got a 30% space out here, you can compute what your overhang and your girder spacing would need to be. Does that make sense? Everybody okay with that? All right. But yeah, you don't want a super, super wide overhang, but you don't want a super narrow one either. So yeah, the 30%, that's usually around the sweet spot. Okay. Now let me ask a question. If this is 42 inches, what is this dimension here? Yeah. Okay, yeah. So the flange width, if you recall, the flange is 14 inches. So I propose this is 35 inches. Everybody see that? So if I want to talk about the weight of the taper, this is how I'm going to compute it. So watch this. So 1/2 the base right, times the height. How tall is that that triangle? I propose it's 2 inches. That's the full haunch. Because remember, the haunch goes from the top of the web to the bottom of the slabs. That's the whole 2 inches.
Okay, so do you want us to use 2 for the haunch? Because I know in your presentation it was like 2.
Large haunches would be for like really large girder spacings and really large beams. For us, two's fine. Two's going to be fine. All right. Everybody okay with this? Okay. Now, couple things. How many tapers are on the bridge as a whole? 2. Okay. How many beams are there? 4. Now, everything that I've done, though, is just computing an area. To get a weight, I got to do 2 things. 1, convert, and then 2, that got squanched. Sorry about that. But 150 pounds per cubic foot. Does that make sense? Pretty straightforward, right? Anybody got an answer on that? Over here, this is real. Everything over there, I don't know what's going on. That's so funny. Yes, sir. Well, that's what he was asking. There isn't really a requirement. The reason that we've set one, though, is because I'm representing the decks to be flat. And that's fine for our purposes, but they really aren't. Usually, I mean, you're going to have a crown, like your 2%, for drainage and whatnot. So in order to set deck elevations, your formwork is usually attached between your girders. So the formwork and the slab ends up being a little bit raised. Now, that's one reason. The other reason for having a haunch in general is because your flange, the top flange up here, it changes thickness. So what we'll do is we'll say, well, the flange gets thicker, but we'll sort of say, okay, 2 inches up from the web, that'll be where the deck is. You see what I mean?
Yeah.
So, no, there isn't really a requirement, but generally, you're only providing a haunch just to ensure that you've got an even geometry. Your haunch ends up creeping up, ends up being a little bit larger when you've got really, really long spans and really large girders. Like let me put it like this. If you got a beam that's like, 200 span, 300 span, some massive structure, the top flange in some regions might be 2.5 inches thick. So obviously a 2-inch thick haunch wouldn't make sense in that.
I was just wondering how it was made, because I've never seen it done correctly.
That's a loaded discussion. We'll talk about that later.
So when your flange thickness changes on that diagram,
Yes.
well, how do you account for that's going to change your haunch thickness?
It's going to change your fillet thickness, not the haunch. The haunch is always 2 inches. See, we accounted for the weight. That's a good question. We accounted for the weight right here because we computed that weighted thickness, if you will.
Okay.
Yeah. You had one?
Yeah, no, but as you took a picture of a bridge over the summer, and like the top flange was inside the deck, disappeared, like you can't see it from the bridge.
How old was this bridge?
It's pretty new. Like it's
And they just embedded it?
yeah.
I wouldn't have done that.
And like the ends of it too were like.
Are you saying it wasn't even? The reason I wouldn't do that is because so first, look, there's nothing preventing that, but I think it creates a little bit more of a complication from the fabrication side. But B, you do actually get a little bit of a capacity benefit from having that extended out a little bit. Moment equals force times distance. So separating that out, you do actually get a little bit of a bump in capacity. I'm curious how their formwork was set up, though, to have that just embedded. A little interesting.
It's uneven. I mean, in the beginning, it's outside the deck, and then it goes inside.
That's quality work. I'm sorry. I'm just being honest. I mean, look. Were you a part of that project?
I just happened to be by, it's fairly easy.
Um, I mean, I'm not trying to call anybody out, but it doesn't look like the greatest work. I mean, it looks like that particular project, that the deck could have been set better. You got to look at it like this, okay? An uneven deck thickness like that, and like what you showed me in that picture, if the engineer isn't aware of that, or the engineer didn't design for that, I can almost guarantee you, not only do you have a variable haunch, but you have a variable deck thickness. What do you think that's going to do to the loads? Right? Look at these numbers that we're getting. First, anybody have a number for this? There's a point I want to make. 9.1. Do I have a second on that? Yeah. Okay. So it's not a lot. Okay, that's not a lot. Look at this. Look at the number we were getting for the slab. 983 pounds per foot. That's if everything's done right. You see what I mean? That's, you know, like stuff like that isn't a joke. Well, you might be onto something there, Mr. Lewis. Oh, Lord. Okay. There's one more load that needs to be assessed, and that's SIP formwork. Okay. Now, SIP formwork is essentially the metal deck pans that are used to cast the deck. Now, I'll be frank with you. Some states do not like the use of SIP formworks. West Virginia is a state that doesn't mind them. There's a perception that because it's metal, it's just another thing that can rust. But, and okay, maybe there's some truth to that, but, you know, once the deck is formed and cured and composite and hardened, who cares? Yeah. And if you're getting some sort of like chloride penetration that's starting at the very top and it has penetrated completely through the deck and it's starting to corrode your deck pans, you got a couple more problems with just your deck pans. That's I'm just saying. So yeah. Now for the SIP formwork, one assumption I'm going to make is and I'm going to call it a weight of the SIP forms, but actually let me not do that. I don't want to use W. I'm going to use P. And the reason why is I'm going to assume that the SIP formwork weighs about 15 pounds per square foot. Okay, that is a pretty upper bound estimate, but you know it's not just the SIP formwork; it's the formwork, it's all the connection, you know, the clip angles, the straps, and all that. But even then, it's a little bit on the upper end. You know, you can go find, you know, SIP form manufacturing guys, and typically you'll find like 8 PSF, 9 PSF, 10 PSF. You know, obviously, think about it like this. The wider your girder spacing, the bulkier or beefier, if you will, your formwork needs to be. So, you know, if you've got 8-foot girder spacing versus 15-foot girder spacing, well, there's going to be a bigger demand on the formwork, so you're going to need to use different forms. You see what I mean? Yes, sir.
How do you account for the concrete that gets in the gaps?
That's a good question. When we first, that's a good question. I guess you could say right now I don't want to say I'm conservatively neglecting it. I guess you could say I am. The easiest answer to your question is this. So first off, you actually need the forms. Okay, you need to find Steel Deck Institute manufacturing guide to figure out what forms you're going to use. Once you have that, you'll have the geometry of the form so that you can determine, okay, here's the area of that, you know, little channel. Then the area times the length, you can determine the overall weight. And plus, I don't even think you need to do that. A lot of these formwork guides, they have that listed. But I do want to add another issue. You're bringing up an interesting point within the world of bridge engineering, and there are times that in order to shave weight on the weight of the bridge, a lot of folks will order SIP formwork, and it'll come, but inside the flutes, where you get that little bit extra concrete, inside the flutes, they filled them with basically like foam. It's like kind of like that, you know, the big foam sheets like you get at those. I'm talking about. It's basically they filled it with that because the philosophy is, well, by filling it with foam, it's not being filled with concrete. So that is an option, and then you can neglect it. I mean, if you want to account for the weight of the foam, go ahead, but that really is going to be negligible. So that is an option. I'm actually not the biggest fan of it. I kind of think you need to fill the entirety of the form. That's just me. But yeah, that comes from going to the manufacturer and getting the geometry. It does, and my advice would be go off of what's in the manufacturer. See, every manufacturer that produces SIP forms is going to produce SIP forms at a different geometry. So if you've got that additional concrete that you want to account for, well then do so. But do so by going off of, okay, if you're looking up PAN 42A or whatever, it's going to have cross-sectional properties, it's going to have cross-sectional areas and so on and so forth. Count up the number of flutes and divide to get an average weight per foot and do the same thing that we're doing here. There's nothing wrong with that at all, and you're raising a great point. But also, don't forget the forms themselves. Now, in order to compute that weight, you need to pay attention to this because this is kind of important, okay? Because you want to make sure you're doing it accurately. Okay, watch this. Okay, first off, the SIP forms, okay, so what was the girder spacing? I think the girder spacing is 10 feet. The SIP forms, they only exist, you know, like you'll have something like that, or what have you, but they only exist from here to here. So how do I determine this dimension? The top flange, right? So 10 feet minus that. Make sense? Okay, now watch this. So here's what I propose. So the weight of the SIP forms is as follows. So 10 feet minus 14 inches divided by 12 inches per foot, right? Okay. Now, here's the interesting part. Let's look at this. How many girders do I have in the bridge? 4. So how many increments of formwork do I have? 3, right? 1, 2, 3. So I propose what you do is you would say, all right, take this distance, multiply it by 3, but divide it by 4. Everybody okay with that? And then multiply it by 15 pounds per square foot. So what I was getting at is if you want to account for that additional weight of the concrete and the flutes of the form, go ahead, but you got to make sure you're not applying it everywhere. It's only where the formwork is. So there's a fly right there. I just want to make sure that the concept makes sense. Say it again. Okay. All right. Second on that? Okay. So watch here. If you're wondering where this is going, I want you to know where this is going. So help me out. So here's a summary. All right. So what was the weight of the girder? Actually, let's just do this. What was the girder? Y'all have this? No, yeah, pounds per foot. Yep, you're right. Does anybody have this handy? What was the details? The slab? What's that? Okay, what was it? 0.0? All right, there was the fillet and the taper and then the SIP. Now I know the SIP, that's right here, that's 99.4. And the taper was 9 point something, like 9.1. So summing these up, what is DC1? $1291.2. Do I have a second on that? Okay, so 1291.2 pounds per foot. So this is the DC1 load. What I mean by that is like, and this is, I'll do, my little thought bubble here. So, you know, essentially what you would have is you would have your model, you know, I'll say, for example, and then you would have some distributed load on it. That distributed load would be 1291.2 pounds per foot. So what you could say is your moment from DC1 is WL squared over 8, you know, your shear and et cetera, et cetera. So that would be your dead load moment. Then you'd have a live load moment, it's not, the load combos aren't 1.2 and 1.6, but essentially you would do something similar to 1.2 dead plus 1.6 live to get your moments and then compute your capacity. You see what I mean? So everybody kind of see where this is going. You know, I want you to see sort of the big picture at the end. Sound good? Now, there are two other loads that I'm actually not going to do with you all because I don't think that there's really a necessity to do this, to actually go through this calc because they're incredibly easy. Okay? That's DC1. Okay? DC2 for this bridge is the one thing that's visible in that cross section that we didn't use. The barriers, right? Yeah. So because they're going to be applied after the deck becomes composite. So here's what you would do. Figure out the weight of one barrier, like pounds per foot, multiply it by 2, divide by 4. That's it. Okay? DW is your wearing surface. Now, a very upper bound estimate for a wearing surface is about 25 pounds per square foot. So take 25 pounds per square foot. This is a wearing surface. So 25 pounds per square foot would be multiplied by your roadway width because that's going to be across the entire road. So 25 pounds per square foot times 34 feet, divide that by 4, that is the DW per girder. So there's your DC1, DC2, and DW per girder. It's that simple. Yes?
So do the interior beams, do they truly feel the same load as the exterior beams with the...
Okay, are you talking about dead load or live load?
With the dead load. Like with the parapet walls and the barrier walls, those are more towards the exterior.
That's a good question. And I'll answer it by saying this. If I had 12 beams on the bridge, like a massive number of beams, what I would probably do as a bridge engineer is I would distribute that barrier load to the exterior girders and then the next one over. So, you know, if there were 12 beams, what I would do is I would take this and say half goes here and half goes there. And then take this one, half goes here and half goes there. Now there's a whole bunch of other beams, but this only has 4 beams. So because there's such a small number of beams, I think it's safe to just distribute it evenly. Some bridge engineers will distribute it to this one and this one over. Some will just say it all goes to the exterior beam. I don't know that there's really a right or wrong answer to that. I mean, the code is fairly, in terms of your analysis methodology, as long as it's sound and backed up by reason and what the code specifies, you can kind of do what you want. Like, you got to understand, let's talk about what I mean when I say analysis. Our analysis is WL squared over 8 for a simply supported beam. That's analysis right there. Load, moment, period. That's a simple analysis. A complicated analysis would be a full-blown 3-dimensional finite element analysis on, you know, every single element and just getting the stresses from there. You can do that too. I wouldn't do that on a 120-foot creek crossing. I would on a multi-span horizontally curved flyover in an Atlanta interchange. Like that I definitely would, because that's complicated. This isn't complicated, so what you all learned in structural analysis will work just fine. That's what we're building. You know, most of our bridges, that's what they are. So, does that make sense?
So if you only use the outside girders, that would change your
You'd have a different DC1 on the exterior girders than you would the interior girders.
divide by 2 at that point.
Well, no, what I would do is I would say, okay, I would have 2 different DC1s altogether. I'd have a DC1 for exterior girder. You know what I mean? I'd treat them differently. In that instance, what I would probably do, I don't even know, depending upon the loads, if you would need to even, quote unquote, design the interior girders altogether. Just design the exterior ones and Control C, Control V, you know?
Less work to do.
Basically.
Or not less work, just less times.
Yeah, yeah. I mean, typically what I recommend for simple, straightforward bridges is design for a worst case and just copy paste. Man, that rhymes. That should be a thing. There's a barrier.
That is kind of a stupid question to require covered concrete, but would you not need to account for the steel that's going into that?
Now we talked about that.
No, we did. I just can't remember what.
We use 150 pounds per cubic foot as opposed to 145.
Okay, but that's what's confusing, because I know we use that, but why would that not be different if you're using, say, number 2 bars versus number 8 units?
Because you're still, I mean, you're right. It's an estimate, but it's not like because we throw rebar in the slab, it's not like we're changing the slab from a concrete slab to just one big lump of steel. It gets a little heavier, not drastically heavier. And plus, here's another thing. Okay, you got to be aware of something else too. All right, got to be aware of this. Would this be the moment that we use, or is it this moment times, you know, like 1.2, and then the live load moment times 1.6, and for bridges it's 1.25. Remember, we recognize that when it's all said and done, there is still uncertainty associated with the loads that we use. That's why we don't use raw loads in RFD. We take those loads and we adjust them. I think the live loads, for all the provisions and all the details and code specs present to us, there's still a whole hell of a lot of uncertainty associated with it. That's why we take the live loads that we compute and we bump them up 75%.
Are there any kind of factors safety for poor construction installment?
Yeah, it's called engineer on site. If you were on a site, would you allow that to happen?
I wouldn't want to, but I've been told to keep my mouth shut before.
There's a difference between being an intern and being the one with your PE stamp on the job. There's a big difference. I'm serious.
I only saw RPE once in 10 weeks on the job.
Don't tell me that. I don't want to know stuff like that. I don't want to know that stuff. Hold on. Let me see. Man, I kept you all a little longer than I thought I would. But I am done. I'm not going to talk about live loads. You go home. Yeah. Yeah, I'm going to stop this one.